Good afternoon, everyone. Today we're going to be talking about models, incidentally my favorite topic. I'll be going through a lot of case studies. I'm going to be talking mainly about water models today, but really the concepts are applicable to any type of model. I'm trying to focus on what are the best steps in order to come up with a model that is reliable, that you can actually make some sort of a prediction that you can then assess in terms of risk to VCs. And in an EIA setting, that's essentially what we're trying to do, is we're trying to make some prediction about the future that will help us understand what is the risk to a specific VC. At the end of the day, that's really what we care about. So there's a lot of different steps that go into this. Not all of these steps are applicable to all models, but generally these are the kinds of steps that you would want to take if you're doing any kind of model. And it doesn't really matter whether it's a water model or a wildlife model or an air quality model. It's all sort of the same basic procedure. So the photo of the day is Dinosaur Lake. It's kind of pretty. Presumably Site C's reservoir will look something like this one day, but we'll see. So I've got a bunch of modeling topics. This will almost definitely take more than today, but I'm going to try and get through sort of the first half of this list. Starting with the very basics, what is a model? And the reason I'm going to actually start that basic is because there's lots of different types of models, and it's often not clear what somebody's talking about when they say, I've got a model. And why use a model? There's lots of different reasons we would use a model. In an EIA, it's fairly straightforward, but there's lots of other purposes for models. Some types of models, and then I'll go through sort of the steps involved in developing a model. So there's a few terms that I'll probably use. So stochastic or probabilistic. It's essentially a method of drawing from some probability distribution, some numerical probability distribution of some input, so some variable that changes with time, or some variable that can have different values at different spaces. We don't really know. It's just we know that there's a certain variable that can change a lot, and we don't know what it's going to be from day to day. So we're going to give it a whole cloud of distributions, and we're going to run lots and lots of simulations and pull randomly from that distribution one value for every run. So what we then get is a cloud of results, each with this different probability. And a hindcast is like a forecast, except it's in the past. And hindcasts are really important, particularly when we're trying to calibrate a model. Prediction, projections, and forecasts, these are sort of used interchangeably. It's basically just we're going to generate some prediction about the future using a model. And then calibration and validation, these have sort of longer definitions that I'm going to go through in detail, so I'll just refer to the following slides. And then if I talk about parameterization, that's assigning some value to a model coefficient. I'll talk a lot about that as well. And that can be part of calibration, or it can just be part of the model setup. Okay, but to start with, what is a model? There are lots of definitions, lots of different types. I'll start with my favorite, Zoolander. That is definitely not what we're talking about. And then we have bench scale models. These are important. But again, if somebody says I have a groundwater model, and that's all they tell you, you don't know whether they've got a bench scale model or a computer program. So we need to be clear about what we're talking about. This is a conceptual model. This is something we make before we do a numerical model, but it's still just a different type of model. So really, when I talk about models in this talk, I'm talking about a numerical model, which is shown here. My definition is shown at the bottom, and I'm just showing you the other ones to kind of illustrate the point that even in the scientific literature, you'll find tons of different definitions of what a model actually is. And so my definition is a computer program that simulates a simplified representation of reality expressed as a set of mathematical equations using field measured data to represent values of variables assembled with enough complexity to estimate driving processes and conditions of interest, usually in the future under scenarios that do not presently exist. And there's some key points in every part of that. So number one, it's a computer program. We're talking about a numerical model. And even within that definition, you'll find some people refer to the software that you're using as a model. So GoldSim is a model. Excel can be a model, MATLAB can be a model, and sometimes people are just referring to the specific part of that you built. And again, both of those terms are correct. You just need to be really explicit about what you're talking about. So expressed as a set of mathematical equations. So virtually everything that you're going to put into a model is going to be some sort of an algorithm or some sort of a mathematical equation. Even if it's as simple as summing up a bunch of sources, that's still a mathematical equation, or something highly complex like some of the examples I'll show. It's really just a matter of scale, but those are all sort of the same thing. It's a mathematical equation in a piece of software that you're going to add some inputs to. The next point is using field measured data to represent values of variables. So if we don't have field measured data, the model's kind of useless. It's really just a guess. There are some models like that. They can be useful in certain circumstances, but it really relies on some input data to drive all of the processes. And then enough complexity to estimate driving processes. So it has to be complex enough that you're capturing the complexity of the system, but not so complex that you sort of lose track of all your variables. And so probably the most complex types of models are basically the global climate change models. They have tons and tons of nested models within them. They're super complex, and it would be extremely difficult to track one variable through the entire model. There are some models like that we use in EIAs, and I don't recommend it because at a certain point the model is so complex that you just can't make any sense of any of the variables anymore. So the sub-bullet under there is valid under a set of assumptions which should be both well understood and transparently described. So no matter what sort of model you have, you're simplifying a natural system. You're absolutely going to have some assumptions, and it's often difficult to even understand as the modeler what those assumptions are because it's often not clear. So an easy one is if you're modeling a river, often rivers are done in 2 dimensions, meaning that we care about what's happening as water moves downstream and perhaps side to side, but not vertically, because rivers are almost always fully mixed vertically. So that's our assumption. It's a 2D model. We assume that it's vertically mixed. It can be really any type of assumption that goes into your model that has simplified it from a natural system into the mathematical code you're using. And the key point there is transparently described. So no matter what type of model you're doing, but particularly in an environmental impact assessment, you need to be really clear about what your assumptions are. Otherwise, people are going to read it and they're going to basically think you're hiding something because you've made these simplifying assumptions, but you haven't actually told anybody about them, and it just doesn't look very honest as a modeler. So it's really important to put all of your assumptions into a report. So back to what is a model. So these are a few examples of numerical models. The top left, I'm sure you're familiar with. It's a simple Goldsim model. There are some input data. In this case, it's just one set of input data feeding into some sort of an algorithm, which then we look at in some sort of an output data. So that's the absolute bare bones, simplest type of model. Below that, I'm showing an Excel model. It's a little more complicated. It's got a bunch of fields that you input data into, and then in the background all the different spreadsheets are doing the calculations and producing that graph you see here. So Excel can be used to model just about anything. It's not the best platform, but it's a nice generic platform. On the right, I'm just showing, this is from the matrix, but really there are a lot of models that look like this. This is just binary code. There's a lot of models where the algorithms are not visible to the user. So you have some sort of an interface, and in the interface you'll input your input data and your coefficients, but then all of the calculations are done in the background. All of the things you input are converted into some binary code. They're calculated using code that we can't even see, and it comes out with some output. Now these are sometimes referred to as black box models because nobody actually understands how they work. But the really best versions of these have really, really thorough model manuals where you can look up every single calculation. They're usually about 500 pages long, and you can understand exactly what the heck is going on when all that binary code is churning through. So the most heavily developed models are all like this. They're usually written in Fortran, and they're usually developed by the US government for the most part, or universities in the US, almost all of them. And so they only have trust because they've been used many times and they've been reviewed many times by other people. But typically, if you're using one of these models in an environmental impact assessment, you need to make sure that it's really well documented, or people will just not trust it. They'll say, that's a black box, we have no reason to trust it. So, what are some different objectives for using a model? So, in an environmental impact assessment, the number one reason, predict the possible or likely effects of a future development. And so that can be anything. It can be wildlife range, can be concentrations in air, can be odor, basically anything. Anything that we have some method of applying a numerical formula to. And ultimately, those model results will be used to calculate the risk by a risk assessment team or person, or usually not the same person who did the model, but it can be. But usually the risk is calculated by somebody who's just a specialist in risk assessment. And so again, that's why it's really important to document all of your assumptions, because if the person who's doing the risk assessment doesn't even understand how your model works, your risk assessment is going to be out to lunch. And that is often a big problem with EIAs, is that the risk assessment team themselves doesn't fully understand the model. They put out a risk assessment, and then people start reviewing it, finding problems, and they have to sort of backtrack because they didn't realize certain assumptions were made. So really important not just to communicate to the public and reviewers, but within your own team. Sometimes models are used to understand baseline conditions. A good example of this is Site C. They did a baseline model, although they didn't model pre-development of the WAC Bennett Dam. But they did model the baseline conditions, because often a model is used simply to understand the present system, because a model is essentially a big calculator and it can tell us things that we can't really understand without using that type of tool. Another reason is to understand the driving variables. So again, climate change models, that's precisely what those are for. They want to understand, is it carbon dioxide changing the temperature? Is it aerosols? Is it water vapor? What the heck is it? And a good way to figure that out is to use a model, change the variables within the model, and see if the model responds the way nature responds. And that is essentially a hypothesis driving type of modeling exercise. Another one is to determine reasonable compliance limits. So as part of an environmental impact assessment, you'll make some predictions. The government will want to know, how can we verify this later on to make sure that even though you've made these fancy predictions with your model, we want to know in the real world that concentrations or whatever your variable is behaving as it should. And not only does the government want to understand that, but they want to put compliance limits on so that the proponent is now bound to maintain those limits. And so models can be used for that. They often are. Optimizing mitigation or treatment, that's another really big use, and that's often done in the background as part of an environmental impact assessment. So let's use a discharge to a lake as an example. Say the city of Kelowna wants to upgrade their wastewater treatment plant, and they want to know, if we install a certain treatment for phosphorus, is it going to make any difference to the lake? And so we can run a phosphorus model in the lake, and rather than having to do trial and error, building things and trying different things at the treatment plant, we can run a whole bunch of different scenarios, come up with a cost-benefit analysis that says, treating your phosphorus down to a quarter of the present limit will bring it down in the lake a certain amount. That'll cost you X dollars. Another scenario would bring it down a certain limit, and it would cost a different amount. And so you've got a true cost-benefit analysis without actually having to go out and do trial and error with big infrastructure. Now, they're not always 100% accurate, obviously, they're models, but as a way of trying to understand a system before you invest in a lot of infrastructure, they're definitely the best tool we have. And then we can also test the sensitivity, and we'll talk a lot more about sensitivity analysis next week, so I'll leave that for now. And a key point about models is that there's nothing that a model does that you couldn't do manually if you had a lot of time. In other words, all of the algorithms or calculations or anything in a model are just simply formulas that we can calculate either by hand or in a spreadsheet or some other method. It's just a lot more efficient to use some Fortran code or something that runs millions of iterations per second. And on that note, it's really good practice to always do some hand calculations. No matter what you're modeling, do some hand calculations on the side and make sure you get something reasonably close. If you don't, you've probably got a major error in your model. Even if a model is really complex, you can usually use some very sort of coarse estimates to make sure that you're in the right ballpark. I'm not going to talk a whole bunch about conceptual models. I just want to remind you about a couple of points about the conceptual models. It should have a similar level of complexity as what you're actually going to put in your numerical model. And so here I'm showing two different conceptual models. One's very simple, one's very complex. But in both cases, these are exactly what went into the numerical model. And looking at this, you can sort of tell, the one on the left is pretty simple. It's just got the very most important physical and chemical features. The one on the right is very detailed, and it's got a lot of sort of redox chemistry going on. And that sort of conveys to the reader what they should expect if they were to look inside your numerical model. And as a bare minimum, you want to show the inputs, the processes that are going on inside the model, and the outputs. They should be spatially representative, but that's not always possible. So for example, the one on the left is kind of a cutaway view of a pit lake. The one on the right is not spatially representative because it was too complex to even try and put some space into it. The only realism there is that there are 3 vertical layers in the model, but certainly nothing within those layers is occurring anywhere in relation to the space it takes up on that figure. Ideally, illustrate the physical domain. So the physical domain should be similar to your study area. I'm going to talk more about that when I get into model setup. Even within numerical models, there are a lot of different variations. Probably the most common are mass balance models, essentially conserving the mass of some substance through some unit of space. So if you think about an air quality model, there will be some stack emission or a fleet of mine trucks or whatever it is, something that's emitting contaminants into the air. We want to track the mass or concentration of everything going up the stack, and we want to trace it through the atmosphere until it lands on Earth or until it's completely dissipated into the atmosphere. And that's essentially a mass balance with some dispersion equations. But most of the models that are out there are based on a mass balance of some sort. Some sort of input goes into the system, it undergoes some transformation, and it comes out the other end either at a different concentration or a different form, or something's different about it. Otherwise, we wouldn't need a model. And we want to use that to make our prediction about the future. The next is physical models. So physical models essentially take the fundamental properties such as momentum, and they use that to calculate the movement of something. The ones I'm most familiar with are hydrodynamic models. What those do is they calculate the movement of water through a large system, a river or lake, and they do that by breaking the lake into little tiny pieces, calculating the momentum based on wind momentum, flow from upstream, any other type of momentum that's acted on that cell. It transports it downstream or downwind or wherever it's going. And these are all based on just fundamental equations. There are statistical models. So these are usually based on some observation. Hopefully it's a causative correlation, but not always. We don't always know for sure. Essentially, we see some variable, whether it's maybe some habitat, some type of berry, seems to be correlated with the presence of some herbivore, and based on our correlation of this amount of density of this berry, we can make some prediction about how much of the herbivore it can sustain. And then we have empirical models, which are similar. Empirical models are just based purely on observation. We don't necessarily need to know the algorithm or the mathematical formula that drives something in an empirical formula. We just know that when we observe one condition, another condition is often found with it. One example would be an empirical flow model. These actually usually are based on an algorithm, but they don't need to be. So for example, if you've got a river, it goes through a weir, the water is channeled through there, and then we can relate the level of the water behind the weir to the flow going across. So usually that is done mathematically, but it doesn't need to be. It can simply be a lookup table. At a certain elevation, we get a certain flow. At a different elevation, we get a different flow. And one value of height leads to this value of flow. Now, the thing to remember about empirical models is they're only valid at identical concentrations to where they're observed. So for example, in that weir, that would only be valid for that specific weir or another one that's identically shaped, sized, and everything else in a similar circumstance. So empirical models are used from time to time where you have a large data set. You don't necessarily understand exactly what's driving the system, but you do know that X leads to Y. Then we have risk-based models. These are usually statistical. We can predict the likelihood of some outcome based on a range of probabilities. Usually we have a stochastic model and we want to understand, is there a 10% risk we're going to exceed a threshold? Is there an 80% risk? And if so, what is the consequence of that outcome? And then we have generic models. So GoldSim is a generic model. You can model economic forecasts, the spread of disease, flow of water, anything you want. Excel and MATLAB are the same because they're just platforms. You have to enter everything. You have to enter the algorithms. You have to enter everything about it. But they're set up in ways to help you do that. I'll give a few examples here. So this is a model called the General Lake Model, and just kind of showing the complexity in this model. It's a physical model with a coupled mass balance. And so some of the processes that you can see are wind stirring, which will mix up the water. You can see surface mixing under the water and different layers forming. Those different layers will affect the mass balance of any chemicals coming in. It'll affect the concentration of the water coming off the ice because the really fresh water will stay along the top. It changes the light penetration, and you don't have to memorize any details of this model, but just kind of as an example of what I thought was a pretty good conceptual model showing everything inside that model that we care about in one nice little spatially sort of realistic figure. We can also use a model just as a fancy calculator. So for anybody who's taken geochemistry, this is just showing calculation of solubilities based on lots of different forms of aluminum. And again, there's nothing in this that you couldn't do by hand. This just kind of puts all the calculations together for you, makes it a lot easier. Okay, so model domain. Model domain is really the spatial extent of the model. So ideally, this would be the same as the spatial extent in your EA that you've determined for your valued component, although you might actually want to make your model a little bit bigger, but definitely not smaller. So the reason you might want to make it bigger is because if you're assessing some effect on a VC, you want to make sure that your domain has actually covered the entire area where that VC could be affected. And really the only way to tell that is to go a little bit beyond that and make sure either nothing's changing or it's reaching background values, or depending on how you're assessing it. But you want to actually make sure that you've gone far enough or a bit further. Often you can have different models nested together. And so the one on the right here, I'm showing three different models nested into one, and all three of those models are completely separate. They work in completely different ways. The one at the top is, you can see the grid there, that's a hydrodynamic model, like the one I showed, the General Lake model. The Athabasca River model is a two-dimensional dispersion model, and it's mixing everything that's coming in from the right, which is a mine water balance model, which is essentially just a big mass balance. So you have different models, each one sort of fit for purpose. You have to make sure they fit together, and I'll talk a lot more about model linkages next week. Another type of model domain, so this is a 2D model grid. This is another lake model. This is looking at it from the side. And so what this does is it breaks the lake up into little tiny cubes. And what this is showing is what the model is actually calculating at each point in the little cube of space. To set up a model like this, you set up the grid at whatever size you think is appropriate, and that's something you'll basically learn through experience. You set the model grid up in order to capture the processes of interest, and in this case we're looking at momentum, and so it's showing all the different variables at the bottom, so velocity, dispersion coefficients, density, temperature, all of the things that are going to affect the water movement. Basically the 11 variables down there are calculated at the points shown on this grid, and for every time step the model will calculate all of these variables for every point in the model, and then it will iterate it because every grid cell is affecting all of its neighbor grid cells as time moves on. So it'll calculate it for every grid cell, then it'll recalculate it based on the new values that it's just calculated, and it will continue to redo the calculations, usually hundreds of thousands of times, until it gets what's called a convergence, meaning that all of the values are no longer changing. In other words, the values in one cell are no longer affecting the values in its neighbor cell because it's iterated up to the point where all of those effects have sort of balanced each other out. Okay, so we've got our model domain. We've set it according to where our VC is potentially going to be affected, or possibly a little bit larger. And now we need to start getting inputs. And just as a side note, hopefully everybody who's doing the model in the lab has done this already, found the inputs, and you've probably found that inputs can take a number of different forms. So the most common is usually a time series. And so I'm showing, again, a really simple GoldSim model here with three different types of inputs. A time series is the most common type. The second shown there is input 2. That's just a statistical probability. And again, that's used in a stochastic or probabilistic model. And then the one shown at the bottom is, I think that's a constant value. No, that's a time series. Top one is a constant value. But anyway, there's different ways of inputting these values into a model. We just need to know sort of what is our data set, how are we going to convert it into something a model can read. So if your model is running across time, then your input should also run across time. If you're running a statistical model, then your input should be something reflected statistically. Some of your model inputs may also be constants. For example, a surface area of something that doesn't change, or it can be something that changes from scenario to scenario. So if you're looking at a disturbance area of some project, that will have a certain value in the base case, usually either 0 or a very small amount that reflects exploration or something that's happening in the baseline. Then you'll do an assessment case, which looks at what is the planned footprint of this project, and you might look at that at numerous points in time. And you might also look at a cumulative effects footprint, which is accounting for future expansions, future projects by neighbors, and all of these other things. So your model inputs generally are going to be something that was measured either by, could be yourself, usually not, as the modeler. It can be your company, it can be government data set. There's lots of different places you can get input data. But the step here is usually to convert it into something that makes sense according to the timeline or the sort of statistics that you're actually going to be modeling. So here's a quite a common type of model input. This is a time series of meteorological data. And you can see the first column is the time or date, or combined time and date in this case. So we have hourly meteorological values. These are often just downloaded from a weather station at an airport or something. And we have this long time series that the model will read. And so other types of inputs would look the same: flow, concentration, whatever. And pretty much all models will read this type of input. Some have lots of other types they'll read, but usually Excel spreadsheets are by far the most common type of input. And so, for example, GoldSim can read an Excel sheet directly, or you can enter the same type of data into a sheet in GoldSim. So basically your inputs are values of any variable that can influence the system. What we don't want to put in is some sort of a variable that's actually being calculated by your model. That's called forcing your model. If your model is forced, it really loses predictive value, because you're no longer letting your model calculate variables based on sort of the inputs to the system. You're now sort of manipulating the system. So in other words, if you are trying to calculate the flow in a river, you want to put in the flows in tributaries, flow far upstream. Your model might just sum them up, and then you measure somewhere downstream to make sure that it's actually, your model's giving you something similar to what is actually measured, as opposed to inputting the flow at that point, in which case you're just forcing your model to follow input data. So it's a fine distinction, but you definitely want to make sure that your inputs are really just at the boundary of your model domain, coming into your model and not within that domain itself. So that would apply to weather, flow rates, any type of material flow, which can be an air concentration, a sound. Your input can relate to industrial activity, disturbance areas, can be constants. It really can be anything, but the key point is that it's at the boundary of your model, coming into your model, and not inserting some driver or some variable that's actually in the actual calculation or overriding the calculation. So GoldSim has a nice feature which allows you to input stochastic model inputs, and I'm showing just two different things here. So on the left, this is a normal distribution, and essentially what's going to happen here is you've got this normal distribution. You know that you've got, say, a concentration. I'll use magnesium. Magnesium in a river is often normally distributed. Most chemicals in the river are not, but there are a few that are actually normally distributed. And so we know that the concentration is going to be somewhere between 2 and 8. Most likely value is 5. So we can run 1,000 simulations. The model will pull a different random value from here every time. Now most of the time it's going to pull something close to 5 because that's the most frequent. We can see that from our chart. And in the end we'll end up with some sort of a probabilistic outcome. Where that has value is when we've got a bunch of different inputs like that. We know that they're all going to be in some sort of a range, but we don't know what they're going to be at any given time. By running hundreds or thousands of scenarios, we can look at what is the most likely outcome. And then on the right here, I've just hit the drop-down box just to show all the different types of distributions. So I'm showing the normal, but there's lots of different distributions you can use. You really need to just pick whatever is reflected by your actual data. So I mentioned that most chemicals are not normally distributed. Most are log normal, meaning that they have a certain concentration that they're normally found in, which is usually fairly low, but then they will increase at a very low frequency to extremely high concentrations. So most metals, for example, can vary by hundreds or thousands of times their normal value, but vary infrequently. So that's called a log normal distribution. And again, there's lots of different types you can use. You just really need to know what sort of distribution your input follows. So I'm going to skip ahead to outputs. I'm going to talk more about model setup shortly, but before you proceed down the road of setting up your model, you want to think ahead to what is it you actually want to output. So what are you trying to demonstrate? What are you trying to understand? Does your model have the right units? Does your model look at absolute change or relative change? These are all important questions when we go to do our assessment, because some things we care more about in terms of absolute values. So for example, if there's some threshold, if a certain population of moose can tolerate a habitat fragmentation of 80%, then we care about that absolute value of 80%. If there's some other threshold, which is really relative to current conditions, you can disturb something a certain amount and then you've passed the threshold, then we're talking about relative change. So depending on what it is we want to show in the end, we need to make sure our model is set up properly so that we can actually show this at the end. And so I'm going to talk about 5 different types of model outputs, starting with the most common, which is time series. So time series are very useful in terms of understanding the long-term changes, but I'll talk about some of the drawbacks shortly. So in this example, these are concentrations in mine waters, so copper, molybdenum, and selenium, and the green bands are showing probabilistic uncertainty. So the black line is the median prediction, and the green bands are 5th and 95th, and the light green is 25th and 75th. And then on the left, we're showing the actual observed concentrations to date. So in other words, this mine has always had concentrations in their mine waters within this range in this box and whisker plot, and this is what we're predicting in the future. And the blue dots are actually observed. So this is showing the observed and the prediction. And then these are showing just another way of doing the model, which is based on geochemical lab tests. So there's quite a variation, but what we want to take away from this is, number one, are these concentrations going to be at some harmful level? Number two, do they match the historical data record? Number three, what's our uncertainty here? And so we can get a lot of information from a time series graph. Now, what we can't get is the actual values of certain predictions. So you can't really read those off a graph. These give you kind of a good understanding of the overall system, but not really something you can use in an assessment often. You need the actual predictions at a certain period. And so what this table does is it looks at different snapshots in time. This is actually from a different EIA. It's actually from the Tech Frontier EIA, the one that was in the news last week. So this is looking at concentrations in a river downstream of the Tech Frontier project, immediately after it's built, at the end of mining, after it's been reclaimed, or that one's after it's been reclaimed, and this is 100 years later. But the reason we need to do a table like this is because reviewers want to look at exactly how a certain concentration at a certain time will compare to guidelines. And so we have a bunch of different guidelines in here. We have the chronic and acute water quality guidelines, chronic effects benchmarks, and then we have natural variability. So this is essentially the historical concentrations in the creek, and then a modeled reference. So this is another example of where we actually went back in time and did a baseline model, because when we do these future predictions, we want to separate, are we showing a difference between the real system and a model, or are we showing a difference between what the model predicts on one date versus what the model predicts on another date? And so these are actual measured concentrations, and these are a modeled history. And you can see they're pretty close, but not exactly the same. But this just gives us more of an apples to apples comparison. Now these tables are horrible to look at, they're terrible to review, but they're definitely necessary, and they're often what a lot of the reviewers will go to first, to kind of look at where are the big exceedances of thresholds, what's the magnitude, and we can't really get the magnitude off just a graph. So we need to put tables like this in pretty much every EIA. And I'll also mention, this is one of about probably 50 or 60 tables like this. And so it's a real big job to go through and make sure every number in here actually makes sense, because if you have one number that doesn't make sense, people will find it. So another one is model attribution. So again, I mentioned climate change models. That's often what they're trying to do. What are the driving forces in this system? This is an example of different loadings to a lake. And so what we were able to do with this model is to look at every chemical going into the lake and understand how much of this is background. So as you can see, the background amount varies, and these are all relative amounts. So this tells us nothing about concentration, it tells us nothing about thresholds, it tells us nothing about potential effects. It's purely what is causing the concentrations that we see. And so we can use models to kind of break apart what is driving this system. And as you can see, there's differences in different chemicals. So this is variability in the background for ammonia and phosphorus. Nitrite is coming from effluent. So that really helps us understand what is, what can be mitigated, what should be mitigated, where do we focus our efforts. Another type is a visualization. This is a plume model. These are used a lot in air quality models, but they're used occasionally in water quality models as well. This is a model called Cormix, and interestingly, this is actually a statistical model. What they've done is they've looked at hundreds or thousands of different types of discharges. They actually built this based on air discharges and then converted it into a water model. What it does is it calculates the direction and shape of a plume. And what it does is it looks at the densities, it looks at the velocities, and it applies a different statistical equation to this plume at various points. So in this example, we have a near field mixing, which you can see that the figure changes at 3 different points. So it's applying 3 different statistical approximations. And it's not actually predicting a concentration anywhere. It's just saying that, we have these sort of ranges where we're going to see a certain amount of dispersion. And again, it's based on similar experiments, usually sort of bench scale experiments, which are then extrapolated up into the real world. But what it does is it really helps us when we're trying to set a monitoring program, for example. If you're trying to predict an effluent in air or water, it's going to move with that air or water, and it's going to move at different rates. It's going to move at different sort of shapes of a plume. And so we use a statistical model like this to give us a basic understanding of what to expect, and then we go out and monitor. So in this example, this is a buoyant plume. It's rising because it's less dense than the surrounding water. And I think this is probably in meters. So what this tells us then is we need to go out in a boat and drop our probe down to about 20 meters in the direction of this plume, and hopefully we find it. Then we can take samples, and that's really the benefit of something like this. It's not so much that it's going to tell us a certain concentration or something like that. It's just giving us a nice representation that we can then go out and verify using field data. So another type of output is a cumulative distribution. I can't remember where in the GoldSim tutorials these kick in, but I know they're covered in there. So essentially what this is telling us is at a given probability, what will be the concentration, or vice versa, what is the probability of reaching or exceeding any given concentration. The way you read these is, so a concentration of 0.2 is about 0.85, so 85% of the time concentration will be less than 0.2. And by the way, this is a log normal distribution. This is what they look like. Most of the values are in a fairly tight cluster until you get to somewhere between 70 and 90% of your values. And then the top 10 or 20 or so percent will be much, much larger, but again, very infrequent. So that's a very useful feature of these graphs, is it kind of gives you an indication of what are the conditions most of the time. So our median concentration here, and again, this is modeled, this is measured, so they're a little bit off. Our measured data, our median value is like 0.02, something like that. Our 80th percentile is somewhere around 0.1. So we know that 80% of the time the values are going to be in this range, but 20% of the time they could be anywhere up to 1. So 5 times higher, but only 10 or 20% of the time. And the reason that's important is because some types of disturbances or effects are acute and some are chronic. So if we're concerned about an acute effect, then we care about every point on this graph. If we care about a chronic effect, then it's really, we're more interested in the more frequent but lower concentrations, because if it's a chronic effect, it means a long-term exposure, and essentially, depending on what sort of threshold it is, at a certain point, these are not long-term exposures, they're not really important. And so that's something we can't really get off a time series graph. And this is, again, what a risk assessment type person likes to see, is a probability of a certain concentration. Not when in time might we reach a concentration, but what is the likelihood or probability of reaching it at any given time. So these have no time component to them. So model calibration. Model calibration can be a big topic. In a simple mass balance model or a simple flow model, you really shouldn't need to calibrate your model, because all you're doing is adding up masses or volumes. But depending on how frequently the data are they measured everywhere? You're probably going to have to make up for some difference, and the way to do that is model calibration. Model calibration will make up for virtually any difference between observed and modeled data, but not all types of calibration are equally valid. So calibration is the process of adjusting model rates, coefficients, and unknown or unmeasured variables such that the numerical model produces a reasonable hindcast match compared to measured data. So calibration is always looking in the past. You can't calibrate anything in the future because you need observed data for your calibration. And without observed data, you cannot do a calibration. Not only that, but you need observed data that are completely independent of anything else in your model. Otherwise, it's not an independent data set and you're not really doing a valid comparison. So what we're doing is correcting for any small uncertainties or differences between the model and the real world. And so the fact that we're doing a model tells us right off the bat that we're doing something much more simple than the real world. And so we can't possibly get a perfect match to what's happening in the real world. There will be some differences. And calibration is the method for accounting for that and also correcting the model for that. I'm going to show some different types of calibration, but a good consideration is if you do some sort of calibration for your model, there should be some physical phenomenon or some physical process that you can explain that calibration. A lot of models use arbitrary scaling factors. Those are essentially pure fudge factors. And sometimes they're necessary, but they have no physical basis. And it basically means we either don't quite understand our system well enough, or we haven't measured our data frequently enough, or there's some shortcoming that we couldn't account for, so we put this fudge factor in there. And fudge factors are horrible in terms of gaining stakeholder trust, and for good reason. Because with arbitrary scaling factors, it's not so much that the modeler is being dishonest, but the modeler is now assuming that these same arbitrary scaling factors will apply in the future, which there's no valid reason to assume that. So scaling factors should be only used if absolutely necessary. And I've put another nicer, eloquent version of a definition of calibration there. You can read it later if you want. But first, I'm gonna back up and talk about an analogy. So hopefully everybody has learned about Beer's law, and if you've used a spectrophotometer or some other colorimetric method, you've probably done some sort of a calibration. And what we do in a model is almost exactly the same. Well, it is exactly the same concept. It's a little bit different numerically, but it's the exact same concept. So with Beer's law, absorbance is equal to the molar absorption coefficient times the molar concentration times the path length. And so the path length is known with absolute certainty. We can measure it, it never changes. So that's nice. The molar concentration of what we want to understand, or the sample that we care about, we don't know. So what we do is we calibrate using known standards. And so our known standards are taken to be known with absolute certainty. And if we've done a good job, we've prepared our standards, they should be close enough that we can consider these to be perfect knowns. And so all that then leaves is the absorbance, which we're going to measure when we do our calibration, and this coefficient, which is essentially the factor that we can adjust. And so we would go to a lab, we would measure some known concentrations, probably that either we've prepared or we've purchased from a supplier, and we'll construct a curve, and ideally that will be a straight line. If not, we may have some interferences or something, but assuming everything's going well, we'll have a perfectly straight line, and from that we can understand our molar absorption coefficient. And now we've got our knowns, so now we can assume this to be a known, and we can assume this to be a known, and we're going to measure this in all of our unknown samples. And so now we can just rearrange that formula so that we can understand the concentration based on those other three knowns. And so that's how we calibrate. Often that straight line will not be a perfect straight line with a slope of 1. We'll have to make some adjustments based on either interferences in the water, the light in the instruments, whatever it is, the detector. Something's going to be a tiny bit off, hopefully not much, but we've got this coefficient, and most calibrations will relate to some sort of a coefficient. And that's precisely what it's for, because nature doesn't behave exactly the way the formula is implying. So models follow the same process, but often in a more complicated way. So using the Site C model as an example, we've got lots of inputs to the river. These are all sort of our input data. These are going to drive what happens in the river model. And then we want another point where we can calibrate. And depending on what we're calibrating, a different point might make more sense. But I've just chosen this point here for this diagram because it's downstream of all our inputs. We have no inputs anywhere near this. So this is now, if we measure what's happening here, we have a truly independent data set, and hopefully our flow or TSS or nutrients or whatever it is we're modeling, we can now compare to measured data here, and we can make our adjustments as necessary in our calibration. So depending on how complex the model is, there may be multiple coefficients. And so referring back to this CQLW2 model, which is the hydrodynamic model that breaks a river or lake into little tiny cubes. This is just one example of one part of the model. So this is the thermal heat exchange. And so the heat exchange is reliant on all of these different functions. Each of these functions has its own calibration coefficients. So when we go to calibrate the model, we really have a problem of many unknowns. And so we don't know any of those values. You can't go out and measure the longitudinal eddy viscosity or the eddy diffusivity. You just can't measure that. That's a calibrated parameter. Same with Manning's N, which is the roughness. All of these things are pretty much unmeasurable. Solar radiation can be measured, but it almost never is properly or frequently enough. Extinction coefficient, that can't be measured. You can relate it to different measurements, but there's no such thing as actually a measurement of extinction coefficient. So these are all calibration parameters. And so the challenge is, how do we calibrate this when we've got, in this case, 2, 4, 6, 7 coefficients just for temperature. We've got another dozen or so for momentum. We've got another bunch for light, So we got tons of these coefficients, and really the only way to do this is iteratively. Fortunately, with this model, it shows some default parameters. So what we would do is we would set the model to the default parameters and then start changing it one at a time. And hopefully we have some sort of a physical basis for doing so. So for example, solar radiation absorbed in the surface layer, maybe we actually have the odd measurement. We're not going to have measurements as frequently as we want. And maybe we can see that at the 5 or 6 times over the past 50 years that they actually measured it, it was quite different from that default parameter. So we start with that, try adjusting that, do another model run, see if the temperature at the surface layer measures observations. If not, maybe we need to adjust something else. So the nice thing about this is the model manual actually lays out which of these coefficients applies where in each formula, so at least we kind of know how they're applied. But as I mentioned, there's lots of black box models out there that you don't really understand how you're even affecting the equations by changing these coefficients. So I've used this as an example of one that's well documented, but always be careful if you are doing some sort of model that you really understand what this parameter means, how it affects other parts of your model, and it's not just a trial and error thing, which can be a big problem if people don't understand these coefficients. What happens is it's called knob turning or dial turning. It's essentially just changing one of these variables over and over again until you get a good fit of the data. And sometimes you can get values of these coefficients that make no sense whatsoever, but they got a lucky sort of 2 wrongs made a right, and now the model looks good, but the model actually doesn't make any physical sense anymore. So then when you go and try and project into the future, you start projecting nonsense. Another one is the nutrient model. So for the group here who's doing nutrients, this is kind of what it looks like this is a USGS model, I think, or US EPA. No, it's a US EPA model. You don't have to do anything near this complicated, but for example, if you want to look at phosphorus, you need to model everything else on here, and you need to do so iteratively because everything here is affected by other processes that are going on. So as nitrogen is consumed, it'll affect the rate of consumption of phosphorus. You have grazing going on, which will remove dissolved constituents. You have all of these processes, and every time a coefficient is changed somewhere along here, it changes everything else on the page. So this is why you need to do lots of iterations. You need to sort of make an educated guess at which part of this is going to be least sensitive to change. So for example, maybe the BOD is not that sensitive to changes in nutrients. So you do all your calibration around BOD first, move on to nitrogen, and then move on to phosphorus, whatever it is, but you need to then go back to the start and see how much you've changed everything else. So that can be a really time-consuming process. And this is just a simple mass balance model. This is from Snap Lake, Northwest Territories. And there is a mine, the mine's now closed, but starting in 2001, the mine started discharging groundwater, which was seeping into the underground mine, into the lake. And as you can see, as soon as they do that, it starts driving up chloride concentrations. And the reason I'm showing this here is because I'm showing chloride and ammonia. So chloride almost always behaves perfectly conservatively, meaning that whatever goes into the system comes back out. It mixes, but it doesn't undergo any sort of transformation. It doesn't settle. It doesn't adsorb onto anything. It's not consumed. And so you start with something simple like chloride. If your chloride has a decent match, you can then move on because that tells you that, number one, your water balance is probably pretty good. Number two, your input data are probably decent, at least decent enough that you can balance something conservatively. And then you move on to something like ammonia. So in the ammonia, you would first do a simulation with all those default rates, and probably the model will be completely out to lunch. And then you need to go back to this figure and go, okay, so I'm trying to simulate ammonia. I don't want to adjust the coefficients too much because now we're getting into unrealistic sort of ranges of these values. So maybe there's something else that I haven't adjusted yet that I need to do first, and then I'll come back to ammonia. So you might need to go and try and do your phosphorus or your BOD or something else. But the point there is that starting with something simple like chloride gives you some good confidence that at least you have a basis for then going on to calibrate the more complicated parameters. In contrast, if you were to go straight to ammonia, having not done something simple like chloride, you have no idea whether your values are off because your measurements were not good, or your water balance is off, or a bunch of other problems which you can rule out by doing a conservative constituent or tracer. So those were chemical calibrations. This is thermal calibration. And so this was from, this is called a compensation lake, when a company removes fish habitat. This isn't Site C, but they had to do the same thing in Site C because they will be removing some fish habitat. What they need to do is to build some habitat elsewhere. And so for that, we used a model to try and understand, will this habitat be suitable? And then we actually went back and calibrated after the lake was built. And so this is showing the data in the lake. This is measured data, but these model results are based on this measured data. So this is a calibration and not a validation, which I'll talk about next. But essentially what we need to do is to come up with some model coefficients that give us the best overall fit, recognizing that there will be times when our fit is going to be pretty crappy. And so these are vertical profiles. This is the lake surface, this is the lake bottom. These are temperature profiles. So from 0 to 20 degrees, you can see that the observed data shows some stratification of the lake. The model is showing somewhat similar stratification on some days. Some days it gets it really well. Some days it just shows it being unstratified, which is the easiest thing to model. But you know, we've got some good dates, some not so good dates, and it's really going to be a matter of trade-offs, because there's no such thing as a model like this where every date is perfect. It just doesn't happen. So we need to look at what are the important dates. In our assessment, what do we care the most about? Usually it's going to come back to the VCs. Well, always it's going to come back to our VCs. So if we're looking at fish habitat, we normally care about late summer when the water is warmest and DO will be lowest. Spring or fall, depending on what sort of spawners we have. And winter under ice when oxygen gets consumed. So what we would do then here is we would look at those specific dates and we would try and calibrate our model so that it's doing the best on those dates, and we wouldn't be too concerned about the rest of the year. We still want it to be good, but overall we really care about those more sensitive dates. And then the plot on the right, by the way, is showing the difference between modeled and observed temperature. And so we often put a number of different measurements on a graph like this. And so on a certain date, the actual lake temperature was here, and the model predicted, the observed temperature was, in this case, maybe 3. The model said it was almost 4, so this one's not so close. These ones are pretty close. And this just kind of gives us a visual overview of where our predictions are. So at higher temperatures, we tend to be higher in the observed than in the model. In other words, the model underpredicts the high temperatures, and it tends to slightly overpredict the low temperatures. And then we can use numerical values to actually make it more of an objective comparison. So the bias, it's showing a bias of -1.1. So overall, it's about 1.1 degrees too cold. Normalized mean absolute error and root mean square difference. So how far, not caring about which direction it is, but how close are we normally? So root mean Square difference tells us that we're usually within 2 degrees, but it doesn't say which way it's off. And normalized mean absolute error, so we're usually within about 13% of the right value. Then the R-squared is just the correlation between the two. So having these objective measures really allows other people to say, okay, yes, that's a pretty good calibration, or no, it's not. In practice, almost all calibration is done by just looking at the plots and doing visual inspection. We almost never calibrate based on those objective measures, but we want to run the objective measures when we're done to verify or to at least communicate what is the difference between the observed and predicted values. I'm going to stop after this slide. This will be the end of calibration, but the main thing that you really need to take away from model calibration, both for your report that we'll talk more about this when we talk about uncertainty, but also if you're out in the real world, either developing a model or reviewing somebody else's model or using the results of somebody else's model, you really need to understand the uncertainty. And one of the biggest sources of uncertainty in any model will be how much calibration went into this model. Because as I mentioned, calibration is a way of accounting for unknowns. And the more that you've had to put in these adjustments to your model, the less certain we are about how well this model will predict in the future. Because every time we put in one of these model coefficients, we're accounting for conditions on the ground today and in the past as we've measured it. And now we're going to apply this model to a disturbed system. Almost certainly there's going to be something different about the future system. Otherwise, I'm not sure why we would be modeling it. And whatever it is about the future system, whether it's somebody's building a dam, somebody's putting in a discharge, somebody's disturbing a bunch of habitat, it doesn't matter. What that means is that the coefficients that we've calibrated in our pre-development model may or may not hold in the future. And because we know usually quite a bit about past conditions, if we're doing a model, our calibrated model is going to represent the absolute lowest amount of uncertainty we can possibly get out of the model. So anything that's done in the future will be necessarily more uncertain than what we've done in our calibration. So if I look at these measurements here, why these are useful now is because I can tell you for a fact I cannot possibly make a prediction that's better accuracy than what we've done in the past. It's just impossible. I mean, you could get fluky, but you can't make a credible prediction that is less uncertain than what you've done in the past. It's just not really possible. So the future is unknowable, which means there's a lot of different things that could happen to the system that you're modeling, whether or not it's even in your model. The best we can possibly do is account for those known changes, but even with those known changes, that means that our calibration coefficients are not necessarily valid, or at least not going to be exactly the same as they were in the past. So I'm going to talk a lot more about uncertainty, but when it comes to calibration, you really want to understand two things. So qualitatively, what does this mean to our uncertainty? And quantitatively, using the types of measurements that I've shown there. How do we, what is our absolute best possible performance we can expect out of this model? Is it plus or minus 10%, 20%, 100%? Our calibration should be used to kind of help us with that numerical accounting for our uncertainty. Okay, so I'll stop there for today.